Welcome to The Explainer. Today, we're diving into one of the most mind-bending intersections in modern science. We are looking at the exact point where fundamental physics crashes headfirst into information theory. We're going to explore whether the universe is simply made of matter or if, at its absolute core, it's actually made of code. It's a massive debate, it's radically shifting how we view existence, and honestly, it's currently keeping some of the world's smartest scientists awake at night. To get us started, I want to pose a question to you. What is the difference between a computer and a black hole? I know, it sounds exactly like the setup to an absurd joke. You might expect a punchline about a crashed hard drive or disappearing data, right? But this is actually one of the most profound, deeply debated problems in physics today. As you'll see, answering this seemingly ridiculous question changes our entire understanding of reality. Okay, let's kick things off with a famous, punchy quote from the legendary theoretical physicist John A. Wheeler. He simply said, "It from bit." Now, it's incredibly short, but it sets up a massive mystery. Wheeler was suggesting that every physical it in the universe, every mountain, every planet, every single atom, is ultimately derived from immaterial bits of information. Imagine for a second if the fundamental building block of a brick wasn't clay, but a line of software code. That is the gravity of what we're dealing with here. Section 1, the information universe, rethinking reality as computation. To truly understand what Wheeler meant, we really have to overhaul our definition of what a computer is. Most of us think of computers as those sleek metal boxes on our desks or the glass rectangles in our pockets. But theoretical physicists look at it quite differently. To them, all physical systems, no matter what they are made of, are computers. Down at its absolute basement level, nature is fundamentally discrete. Every single electron, photon, and elementary particle stores bits of data simply by existing in a certain state. And every time those particles interact or collide, those bits are transformed, which means they're actively processing information. Just like a tiny transistor in your smartphone flips between a 0 and a 1 to run an app, particles act exactly like logic gates in a cosmic computer. Physical existence and information content aren't just casually related, they are inextricably linked. You literally cannot have one without the other. Section 2, It from Bit, John A. Wheeler's radical proposition. This idea was fiercely developed during his time founding the Center for Theoretical Physics at UT Austin in the late 70s and 80s. Now, Wheeler was a titan of physics. He actually coined the term black hole. But later in life, he became completely obsessed with the question, how come the quantum? He was searching for a much deeper, almost philosophical principle beneath the rigid physical laws of the universe. And his conclusion is fascinating. It from bit is the idea that every physical entity gets its very existence entirely from discrete, detector-elicited yes or no quantum binary choices. Okay, I know, that is a very dense string of scientific jargon, so let's unpack it. Think about an electron hitting a screen in a physics experiment. Did it hit a specific area? Yes or no? Wheeler argued that the underlying invisible world, the quantum fields, the elementary particles, only exist because of these discrete, immaterial units of information. Basically, physical reality might just be the user interface, the UI, of an underlying cosmic operating system. In this view, information is the absolute ground floor of reality. But hey, not everyone is ready to hand information the ultimate crown. That brings us to Section 3, or Bit from It. Julian Barber's counter-argument. Science is all about rigorous debate, and the realist pushback against Wheeler's software-first universe is incredibly compelling. Let's contrast these two heavyweights. In Wheeler's view, It from Bit argues that qubits, quantum bits of information, are the primary elements of the universe. Information creates reality. But British physicist Julian Barber counters this entirely with Bit from It. Barber argues that a piece of information, like a digital 0 or a 1, is totally meaningless without a physical structure to actually represent it. Think about it this way. Try eating a 1 that's supposed to stand for an apple. You can't do it. A bit has zero meaning outside the context of a highly structured physical universe. Reality, Barber argues, creates information, not the other way around. Let's break down Barber's perspective a little further here. Imagine a simple grid of 24 possible slots. If we arrange red and blue dots in a maximally varied, complex configuration across those slots, we create structure. The core point here is that structured variety, the specific, tangible way things are arranged and knit together in space, is the true ground of being. Nature's fundamental rule is that science and information simply cannot exist without structured things. Just like random letters only become a meaningful story when they're physically arranged in a specific order, the universe is a set of physical configurations. The semantic information we pull from the universe relies entirely on its hard, physical reality. Whether you personally believe that information creates matter or that matter creates information, modern physics takes the connection between the two incredibly seriously. Section 4. The ultimate laptop. The physical limits of computation. Physicists really wanted to know what happens if you treat ordinary matter as an extreme computer, pushing it to the absolute boundaries of physics. The foundation of this boundary is known as the Margolis-Levitin theorem. The absolute first law of quantum computation is that computation requires energy. Specifically, the minimum time it takes to flip a single quantum bit, labeled as t, depends directly on the energy applied to it, which is labeled as E. The formula dictates that t is greater than or equal to Planck's constant divided by 4e. To pull that out of the math and into the real world for us, the more energy you apply to a system, the faster its processing speed. Think about your own laptop heating up on your desk when you run a heavy video editor or a massive game. Well, the universe follows a very similar rule. Energy drives the speed of the machine. Consider an ultimate laptop based on these extreme physics. Imagine taking just 1 kilogram of ordinary matter, about the weight of a standard notebook, and converting it entirely into energy to power a computer. First of all, do not try putting this on your lap, because the temperature of this machine would be 1 billion kelvins. It would literally be a confined sphere of intensely screaming plasma. But because of the insane energy density, this 1 kilogram box could perform 10 to the power of 51 operations every single second. It acts as a vast array of parallel processors. Each individual bit flips incredibly fast, though communicating with its distant neighbors across the plasma is relatively slow. But what happens if you take that exact same 1 kilogram of matter and compress it so densely that gravity takes over completely? Section 5. Black hole computers. The ultimate serial processors. When a theoretical computer shrinks down to its absolute smallest possible physical size, the gravitational force becomes so intense that space-time collapses and nothing, not even light, can escape. But here is the wild part. It doesn't stop computing. In fact, it becomes the ultimate, most efficient serial processor allowed by the laws of nature. So how exactly does a black hole compute? Well, it functions shockingly like a cosmic hard drive. Step 1 is input. You encode your data and instructions into physical matter, and you simply drop it past the event horizon. Step 2 is computation. As those particles plummet downward toward the singularity, they violently interact with each other, performing computations at the maximum possible rate for a finite amount of time. In a black hole, the time it takes to flip a quantum bit is exactly equal to the time it takes light to cross the hole. This means communication across the system is just as fast as the computation itself. Finally, step 3 is output. The processed information escapes the black hole via what is known as Hawking radiation. Now that last step, the output, has been the subject of a massive, dramatic, decades-long feud in the physics community known as the black hole information paradox. Originally, the classical view dictated that absolutely nothing escapes. Information falls in, hits the singularity, and is lost from the universe forever. But then Stephen Hawking proved that black holes do evaporate and emit radiation. However, he initially thought this radiation was totally random, meaning the information was destroyed, which completely violates the foundational laws of quantum mechanics. We can't have that. Finally, modern physicists like Gary Horowitz and Juan Maldacena proposed a mind-bending solution. Information escapes through quantum entanglement. Essentially, entangled photon pairs materialize right at the terrifying edge of the black hole. One falls in and interacts with the infalling matter, which instantly teleports the information to its partner photon flying outward into space. The output isn't random gibberish at all. It is heavily processed, teleported data. The black hole computes.
Section 6. The cosmic computer. Scaling up to the entire universe. If a black hole can be mathematically mapped and completely understood as a computer, what happens if we apply these exact same physical limits of computation to the largest system we know? Let's scale this whole thing up from a single collapsed star to the entire observable cosmos. Using the same Margolis-Levitin theorem we discussed earlier, we can take the observed cosmic energy density of the universe, including all visible matter, and dark energy, and calculate its maximum processing speed. The result is 10 to the power of 106 operations per second. To put that completely ungraspable number into perspective, that is vastly more operations happening in a single second than there are atoms in the entire observable universe. That is the heartbeat, the raw processing speed of the cosmos. And if we multiply that speed by the finite age of our universe, roughly 13.8 billion years, we arrive at this staggering number, 10 to the power of 123.
That is the absolute total number of operations, the total number of bit flips that the universe has executed since the moment of the Big Bang. Our universe has literally performed the maximum possible number of operations allowed by the laws of physics. Which leaves us with this final, truly provocative thought. We've seen today that information and physical reality are fundamentally, inherently woven together. We've seen that from the smallest elementary particle acting as a logic gate to the densest black hole acting as a hard drive. The laws of physics are ultimately the instruction set of a vast natural machine. So, if the observable universe is quite literally a giant quantum computer that has executed 10 to the power of 123 operations, what exactly is it calculating? I'll let you sit with that one. Thank you for joining this explainer, and keep questioning the nature of our reality.